In this video I'm going to look at a very specific topic area called potential divider equations. So I'm going to start with a quick recap and then look at where the equations come from using Kirchhoff's laws and then show you some examples of them being put into action. Okay, some things we're going to be using in this video so you make sure you remember. So we've got Kirchhoff's current law and his voltage law. We're going to be looking specifically at series. Potential divider equations are all to do with series loops, so we don't need to worry about the parallel law. And of course, we're going to use Ohm's law as well. It comes up a lot in circuitry. So let's dive straight in. Okay, so a potential divider is, as an example of it, is this circuit here. So it's any series loop containing two or more resistors and also has some sort of EMF or voltage source in the loop. So you need that. And at the moment, if we want to do any calculations, we'd need to do it by you calculating the current and then using that. But what if we want to do it faster than that? So say if we wanted to work out what V1 is, what we'd have to do is calculate the current, and then we'd use the current and the resistance to calculate V1. What if we want a way to skip knowing the current and do this faster? Faster is usually better, so let's have a crack. Okay, so the first step in this is actually to work out an expression for the current, and then we can substitute that in for current in Ohm's law. So, first of all, we need to correct this diagram, because that should be a V2, not a V1. And what we need to do is get an expression for the total resistance. And the total resistance is going to be R1 plus R2. We've got two resistors in there, and they're in series. And so we know the current is going to be V, which in this case is V0, over plus R2. We're just using Ohm's law rearranged here. So the current going around this loop is calculated like this. So if we want to know what V1 is, we would multiply that current by R1. Multiplied by R1, and we're going to rearrange that so you get it in its usual format that you'll see it in. And we have a potential divider equation we can use to calculate V1 without knowing what the current is, based only on the voltage from the power source and your resistors, which is really nice. So let's have a look. So we've got that nicely typed out there, and the same thing done for the V2, which is that one there, showing that exactly the same equation works. The only thing that changes is the resistor on the top line, depending on which one you want to know the potential difference across. And now we've got it independent of current. And now to show you some examples and how we're going to put that to use, not knowing what the current is. Okay, so we've got this circuit here, and we want to know what the potential drop is across the 2 ohm resistor. Now, potential drop is the same as the voltmeter reading if you connected it in parallel with it. So, what we're going to do, we first write out our equation, and then we can substitute our numbers in. So we've got 2 over 2 plus 4 plus 5, and if we substitute the numbers in there, so we've got 12 effectively over 11, which gives you 1.1 volt. Now you might think the significant figures are weird, considering we had 1 sig fig there and we give an answer to 2, but you don't give answers to 1 sig fig unless it's a quantum number, so we'll stick with going one more and give 2 in this scenario. Okay, so let's put the equations to use where it's an advantage not to have the current. Before we do that, typed out solution right there. Okay, so the question's asking if we replaced the 5 ohm resistor with a 10 ohm resistor. So this one over here, we replaced this resistor here with a 10 ohm resistor. What would happen to the voltmeter reading across there? So if we first of all write out how we would calculate it, like this. So essentially what we've done by replacing 5 with 10, we've increased this R3, whereas this is the same, this is the same, and this is the same. So effectively what we've done is we've increased the bottom line without increasing the top line. So this overall term here is going to become smaller, and because V0 is exactly the same as well, that means that V1 is going to decrease, and the reason why is we've increased the denominator, or the fancy word for the bottom line of a fraction, but all others are fixed. So therefore the overall expression for V1 is going to decrease. And I appreciate my handwriting is pretty terrible. But there we go, nice and neatly typed out, so that's not a problem.